Just started. So, just to set the context, so today we are going to learn about the history of the computer programs, history of infrastructure, in the sense that how did we start from monolith and now we have distributed systems, and we'll just get an overview so that we know the code that we develop, where does it go and sit and start working, and then also about little bit history about the development environment because um, it is important to understand from where did we start, from bare minimum text pads to today's AI development tools such as Cursor. There are several Firebase, Replit, and so on. Okay, so I'll start with computer programs, and um, it will take about 30 minutes to cover this, and then let us get into like how to set up your Python uh, development environment and so on. Okay, so how does the computer programs work? So that is how we need to. That is where we need to start to any sort of programming, right? So as a layman, we just click on something and then something comes up and then we just use that software. For example, this particular Notepad or Zoom or whatever. So how does computer programs work internally? And let us look at one slide. So I have prepared some slides here. Okay. So the basic components of any given computer is like three main things. One is your hard disk where the files reside. Second thing is the RAM, which is a temporary.
Are
Uh,
you sharing? Yeah.
oh, sorry. Yeah.
We
Okay. I
can
think
only
I'm
see
sharing.
the desktop.
Okay. 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 Hold on. I think I'm sharing the wrong desktop. Sorry. Desktop one.
Yes.
Can you see now?
Yes.
Okay. Great. So yeah, we were talking about uh, computers, how the computer programs work, so that people who are new to computer programs, so they get a context. We're not going to get deep into the the details of how it works, actually works, and things like that. You can read it later. But 10,000 feet overview, any given computer, even your laptops, has three basic things. That is hard disk, RAM, and the CPU. CPU is the one which does all the work. It has like transistors inside that, and it does calculations. Okay. And then why we use the RAM is just because we need to feed the data into this computer chips, and there needs to be something which CPU can access quickly. So that is where we have RAM. So that is why it's called as random access memory, because you can allocate the memory inside the chip. And why do we have a hard disk? In fact, you can just build a computer with RAM and the chip. The reason that we have hard disk is to keep the computer programs in such a way that when you switch off the computer and switch it on, so you can get the data back. Like you can reload the programs and things like that. Without this, we wouldn't be able to, um, preserve the data between the restarts. So this is the basic thing. And then how does the computer actually process it? So it only knows ones and zeros. So what do we mean by ones and zeros is basically signals. But how do we send these signals in such a way that it is in our control? So that is where the programming comes into picture. So initial days, people used to write code in zeros and ones and then feed it into the RAM. And then the processor would pick that up, instructions, and then start processing. So so this is one of the one of the old assembly code, and this assembly code is something which is like, so people cannot remember, or it's difficult to know uh, or generate a stream of bytes, ones and zeros, and feed it into computer. Right? So people started writing some of the routines which can be translated, or which can be be used to generate these executables, or ones and zeros of the signals, which is nothing but the executable. So this is how people started abstracting it, so that you don't have to remember this ones and zeros, and they started writing assembly level code. So this is nothing but an automation of ones and zeros, is what is your assembly code. So, and how does assembly code get into the chip? Is we use compilers and loaders. So compilers are nothing but they read this program, generate this executable, which is also called as an object code, and there is something called as loader. So that loader would take that program and flash it onto the RAM. So that is where your once you compile the program, you get some executable which is lying on your hard disk, and then if you double click it, for example, if you double click on Zoom or any application, it loads into the computer, right? So there is a component in the operating system which picks up that executable and puts it on the RAM, and then the micro chip would start reading the data. So that is how the computer programs work. So we can read it later, how it works. So what we are trying to see is there is a pattern of automation. So this is how you can compare. It's like we are sending the Morse code into the chip. So that is our overall goal as a computer programs. But what is the constraint? Why do we need to learn all these languages, and why do we even bother to um, know about the architectures and software design and all these software related things? Why there is a course? Why there is engineering and so on, right? So that is because these chips, if you want to remember, uh, for example, if you want to write a program to a certain chip, you need to know the chip's architecture. So how does it process the data, and what are its executable or the keywords and so on. So you don't need to know the particular architecture. For example, Intel, AMD, and so there are several chips. So back in the days, if you want to program something onto a chip, one would read the manual of the chip, and then they would understand how it works, and then start writing the programs. So that is not scalable, in the sense that you cannot write a program that is supposed to be run on Intel chip and then copy paste that executable and put it onto the AMD chip, right? So because the chip wouldn't know where to start reading and things like that. So that is where the high level languages like Python, C++, and all these things came into picture. So that is the brief history of how does the, so we can go deep, but that is not necessary as of now, because we need to learn other things. So just remember that executable gets loaded into the chip, and chip does that. So this is how the assembly code would look like. This is an automation. If you want to write a program for an Intel chip, you should know these instructions, and then you should also know how the chip interprets it, and then you should tell that where to start reading it and where does it end and things like that. So this is not scalable because there are like hundreds of chips, and each of the chips are having different versions and so on. So it's impossible for a developer to read all the documents and start writing the program, right? So yeah, so that is how we reached into the assembly code. But the process is same, because no matter what language we use, finally we generate an executable which is understood by the CPU. And the higher as we go higher, it's about automating these bits, say to write an assembly code, and then to write high level languages and so on. So why did we arrive at this particular structure for a code? Like there is high level language and there is like bits. So we moved from bits to assembly level language where we are like attached to the chip in the sense that you need to know the chip architecture to write the program. But in order to use high level languages, you don't need to know the details of the chip. So this is an automation from assembly level to high level languages. So what these compilers of this high level language do is they take care of what sort of chip is going to be used for the executable, and then you can specify during the compilation that okay, this is for this sort of chips, and it would generate the executable based on the architecture of that particular chip. So you can write a program on your Linux box or Windows, and you can specify the computer that I want to generate executable for, say, um, Intel chip, which is running Linux and so on. So you can, but you cannot execute that program on your Windows machine. You need to take that executable onto the Linux, and you can run. So this is taken care by the compiler. So that is how now we can forget about the chips and we can just focus on the program logic. So this is how it looks like. We will talk about this later. Yeah. Okay. So a little bit about cross compilation is just now whatever I explained. So you can generate executable and flash it onto any machine. For example, if you're a hobby programmer with who wants to do, fiddle with hardware, so generally those hardwares like a Raspberry Pi or any hardware wouldn't have the monitor, and you won't have the luxury to open up a notepad and write a program and run it. So what would you do typically is you write a program on other machine, and then you flash that onto your system. For example, all the peripheral devices like mouse, this pen and touchpad, keyboards, all of this does not have the interface to write a program, right? But there are some once you plug in, there are some in terms of programming, there are something which is running here. They understand some things, the movements and all these things, and they transfer it to the. So that is how it is done. But yeah, so these are the things that is at a given computer. So we have hardware, we have like basic chip, and on top of that we flash the OS. Like if you buy say HP laptop or something like that, you install Windows operating system, right? So that is your operating system. On top of this operating system, we have like languages which can be run. So you can write C, C++, whatever it is. And then higher level languages, how does it work is uh, you have a program and then you need to put it onto a certain machine. So now the challenge is, okay, you can keep the source code in such a way that it is compiled once and then you can put it onto any machine. So that is what we want to achieve in bytecode compiled languages, which are, for example, if you just to give an example, if you are writing a program in C or C++, you write program and then you use a compiler like G++ or GCC or whatever, and then you generate the executable directly, and you can run it on the machine directly. Like you can double click on it, or you can execute it on the terminal. But the way languages like Java and Python works is slightly different. So you can write a program, you can generate the bytecode, and you can take that bytecode and put it onto the any machine. For example, you can generate the bytecode on say Intel chip and you can run it on AMD machine. So how it is possible is because there is something called as virtual machine, which is middle layer sitting in between your bytecode and the machine code, which is nothing but the executable. It can translate the bytecode to the machine code. So that you have program portability. So you can simply copy those bytecode and you can run it anywhere, given that there is a particular virtual machine running on that machine. So that's about like program how the computer programs work. So that's like very basic. You don't have to um, go deep into that, but you understand that to generate machine code, we are doing all this circus. So now we don't have to worry about the operating system. We don't have to worry about the chip. So that is what we are trying to get rid of. So this is called as an abstraction in a plain English. So and let's talk about, now we understood like how the programs work, like very in like 10,000 feet overview. And let's understand about infrastructure. So why we need to understand the infrastructure is because once we write the program, it is going to run somewhere, right? So that is why we need to understand the infrastructure. So I'll talk about a little bit about how back in the days how programs used to run, and now how it is run. Okay, so infrastructure. So infrastructure is nothing but like one PC, right? And then you generate you have currently you have keyboard and you write a program and execute it here. So the computer programs that we write, for example, let us take a web application, something like Facebook or Google or whatever. So if you closely look at it, it has like different components like UI, it has backend programs, and probably it has databases and things like that. So all these are different programs, but put together components. So all of this can be run in one single computer. Okay. And next is, okay, what is the constraint and why do we need to move to multiple computers? Is if you start running this web service in one single computer, say probably 100 people can log into that particular application, say Facebook or Google or Gmail or whatever. But if there are 1,000 people using it, so probably it won't support. So you'll need multiple computers. For example, you may need 10 computers. But how far can we go? Like, say, for example, Facebook, probably like 2 billion people are using. So how do we scale this up to a place where you can have as many computers as you want, which supports all these operations, right? So this particular thing where we run all the things in one single computer is called as monolith. Mono is one, lith is stone. So it's a single stone computer. So, and then now the problem is, okay, just imagine you have two computers. Now, either you can put all of this complete stack into copy this stack into two different computers and start running it. Now the problem is like how do you balance the load? For example, there are 100 people coming here and then there are 100 people going here and so on. So there are, you need a network and things like that, right? So that is called as load balancing. So if you try to break this down into different components, now you can have UI running in one computer, backend running in another computer, database running in a different computer. So you can say, I'll just erase all this. So you can, in fact, let us try to arrive at three different computers: UI, backend, and database. So if there is an access layer here, which is like network access layer, and there is somebody who is doing aggregation of all this. So Um, in this is primitive version of distributed computing, because the computing is happening in different computers. Now, just imagine you have what, like, you are running in one computer, and then given the complexity, probably you will have to run it in multiple computers altogether here, and probably backend you might need to have multiple computers here. So just to give an use case, for example, there is a popular person, let's say Elon Musk or somebody like that, and he posts something on the Twitter or Facebook, wherever. So a lot of people are going to like get notification and look at that particular thing, right? So the backend is backend UI database, everything is getting loaded. So how many computers would you require for that? So in order to calculate this, we need to understand like how many people are using it, how many computation units we need, and so on. So this particular entire department comes under infrastructure management. So just to give you an idea, like how does current infrastructure look like? So this is when Google started its service. This was a single computer which was like you could log into Google and then you can do the searching. Okay, there was a single computer, and what we have today is this. This is nothing but a data center with a lot of computers, and each of these like pizza boxes that you're seeing is looks like this. This is like probably more than 100 times powerful than this particular computer. So this is how a data center looks like, and this is just like one row of the data center, and Google has like so many data centers across the world. So this is how the uh, world today looks like from the monolith. So why do we need to understand this particular thing? Is because when we deploy some program, we should understand where does each of these services or each of these component go and sit. So what were the innovations that happened in infrastructure? So we had monolith, that is a single computer. So if you're running a company, and then if you have like monolith computers all over your data center, so it is possible that most of the times that particular data center, probably 80% of that particular data center will not be used at all the times. Say if we are running a cricket match, score service, or a cricket match live broadcasting service, probably only when there is a match you'll be using those computers, right? So because people would log into that service and start watching it, but rest of the times it's always like very minimal. So how do you make use of this the infrastructure so that it can be shared across multiple applications, and it can be utilized optimally so that we don't waste the resources? So in the initial days, like companies like IBM, they bought up something called as mainframe. So here they had like a lot of computers, and then you could go onto their computers, and then you can use those computers and relieve them. So now you have like some like you can use and you can destroy it. So that is like renting a computer for your services. And then next came, okay, so now even in the all these are hardwares, and even here we are not replacing hardwares completely. So that is because each computer would have, we saw a stack, right? So it has an hardware, and on top of the hardware we have operating system, and then on top of this all the programs are running. So once, so far until I think early 90s or so, uh, one computer used to run one single operating system. Okay, so even today it's like that, but you can also run multiple operating system on a single hardware. Okay, so that is done using something called as virtualization. So now you can run something like one operating system here, and you can host multiple operating systems here. So that is where your VMware comes into picture. So VMware is a company which produces this mid layer, and you can install as many as that particular computers can support. So since you have multiple operating systems, you can also run multiple programs here, and you can now you are moving from single operating system to multiple operating system. So this was done, and then there is also another one more layer of innovation is something called as containers. So we moved from single OS to this is called as virtualization, and then we have something called as containers. So what does containers mean is you can run mini stack which will have operating system, all your configuration related to the software, and the executables themselves, which are software, in uh, in smaller capacities, in the sense that you can have a lot of containers running in a single operating system. So this is where you hear all. So one of the pioneers was Docker. So Docker is nothing but one of the companies which is a pioneer in containerization and so on. So we moved from a monolith to say mainframe computers where you can rent, and then you can come to like you can install multiple operating systems, which is virtualization, and then now we are having something called as containerization. So the softwares which are running inside the containers, now there are multiple terminologies, but don't worry about it. You might have heard about microservices. Okay, so you can run these containers in the picture that we saw in data centers. So you could have, say, for example, if you open Amazon, if you have used Amazon for shopping, so if you have to list out some of the features like login, cart, and say checkout, uh, say payment, and all these things. So these are probably running in separate containers, and you cannot have single container to cater to that the traffic, right? Because like millions of people are accessing it at the same time. So there are like hundreds of thousands of containers, login containers probably running in any given data center of Amazon, that is AWS. And then there is like all of these components are having multiple copies, and they're running in the data center. And somebody who is orchestrating this is called as an orchestrator. And you might have heard about like Kubernetes and these terminologies like so Kubernetes. So this is how the infrastructure has moved from like monoliths to containers, and there are companies which build businesses on top of it. For example, I'll just tell you how companies built. For example, IBM started making mainframes. Like, if you want to host your own data center, they would come and install mainframes, and then they will make a data center in your premise, which is called as like on-premise data center. And then VMware is a company which built this virtualization layer, and like they made a lot of money in this because you're saving a lot of CPUs and power, right? And then Docker is an open source, but yeah, they also made good amount of money, and also VMware supports a lot of containers, and now people are moving to containers. Okay, so it depends. Like if you want to run the containers, if you want to run it in a monolith, or if you want to run it in a separate proper hardware, which is a dedicated hardware, or you want to run in a shared hardware. So if you have heard about AWS, right? A company which was a spin-off from Amazon. So they wanted to start, using their own data centers and then their own services. It clicked, and now it's open for like general public to use, and companies are using this. So what they build is they build data centers that we just saw a while ago, and they tell that we are offering so and so services. For example, storage. Um, you might have heard about like S3, but yeah, if you haven't heard about it, it's okay. You can run, say, you can spin off a computer, and then once you are done, it can just vanish. So probably it is called as an like serverless computer or something like that. So you might have heard about Lambda or something like that. So there are several problems in the cloud, which is cloud is nothing but the servers which are not residing in your premise, but somewhere else, and you are using that particular computer for a certain duration, and then like releasing it. So that is taken care by these companies. So one of the services is like Amazon services is AWS, Google services is Google Cloud platform, and then like Azure is from Microsoft, and there are other companies like even I think VMware also has its own thing. Yeah, these are the three big companies. So why do we need to know these things? Is because if you want to scale your application, so you are going to like deploy it somewhere in one of these or somewhere else as well. So you should understand what are these and where is my computer programs going to run. And if you have sizable um, um, sizable like big software which is having multiple components, probably you'll have different components running in different computers, and then these services like AWS, GCP, and all these guys will take care about how do you like aggregate. For example, if you log into UI, how to call the backend services and all these things. It can be defined in certain configuration file. So that will be taken care by these cloud providers. Okay. So that is where we are today in terms of infrastructure structure. So we learned about computer programs, and we learned about like infrastructure because we want to understand where does this uh, programs sit, right? So I gave some examples like login, Facebook, and things like that. So coming to development environment, which is like we're going to work on this particular thing in the full duration of our course. So what is the history of the development environment, right? So in order to do all the software development, what was initially done, and now where are we going towards? Okay. So let me just clear this. Okay. So in order to write a software, obviously you need a software which can take input for that, right? So that is text. So in order to take this text, so if you, if you, I'm sure all of you have used like Notepad and things like that, right? So even before Notepad, so if you have to write a computer program or any text, there used to be, even now we have. So there are programs like VA Editor, Emacs, which is not like UI based in the sense that I'll just show you. Um, so This is an VI editor. So this does not support mouse movements or clicking or anything like that. Uh, Something like this. Okay. And then in order to save this, I need to learn the commands of VI editor, which is nothing but, see, I'm putting some um, statements here, which is a command for write and close. Okay. So I'll just quit it. So this is how people used to write, open the V editor, write the program, and then compile it. Compilation could be taking something like, you write a program and then you'd be writing something like invoke the GCC compiler, and then you take that file, say test.c, and then you'd compile it. So probably the output would be test.exe or test.aout or something like that. So that is an executable which should, so that is generated there, and you can run that program in your computer. Okay, so that is the uh, like primitive editors. So um, when we started programming back in like 90s, so there used to be a executable called as Turbo. So where you open turbo.exe and then you can write C programs, and then there were some interfaces where you can use shortcuts and then run the programs. So from there, what where the world is moving towards, and where are we now? So we know about text padding, text and notepads, and then uh, we got something which can help us to solve the syntax errors, which is nothing but so any program, a given program, it needs to be written in certain fashion, right? You could be seeing like flower base braces and then some statements and something like that. Okay, so something like this, and then you have a list of statements, and then okay. So what used to happen with VI, Emacs, and things like that back in the day is there were like programs, you just look at that as simple text. There were no syntax highlighting, everything was in your head. Like, where did I open the flower bracket? And then where was it ending? And where did the semicolon go, and all these things? So you need to be like hyper aware about your syntax. So learning a programming language was like on peak of on its peak, because everybody who can learn the syntax well and write decent programming, they were like the best in the industry. But the editors which came soon after that will take care about the syntax highlighting, and if there are any syntax errors, it would highlight and it would tell that, okay, you're missing a semicolon, you're missing a keyword or something like that. So why that is made possible? Because each compiler knows what to look for, and the parsers would look for the syntax, and it will tell you how it is, if it's going right or not wrong. So such editors, well, there are a lot of editors. So you must have like Visual Basic, and then today we have like VS Code, which is by Microsoft, and it is open sourced. So you don't have to worry about the syntax. So this is what uh, the problem that it solved was syntax highlighting and probably autocomplete and things like that. And also it would organize your code in such a way that you don't have to remember where this particular code was there. So if you have a directory structure, something like UI and then backend. So imagine that these are directories and then probably tests or something like that. And this is your source code. And there are like several files here. So if you are a developer without these tools, you would have to like remember where it is, and then you'll have to like navigate on command line. and then you have to like open that particular file and use VI or Emacs and then use to write, right? You can write it. So that is how the like Linux was developed, and all the tools that we use today, popular tools were developed using such tools. So now we have got rid of the syntax highlighting and such things. So the next level is so recently you might have seen a lot of videos, which is videos or news where we have AI which is assisting our development. So AI was always there, even in 1970s and 80s and so on. So all the research that had gone into AI was there, and it's still going on. So why AI has become like popular, and this is the new big thing, is because research was there. People knew like how things would work, but we didn't have enough data to operate on those algorithms or those mathematical or whatever. Right. So uh, companies like Facebook, GitHub, and Twitter, and like there are like billions of websites, right? So Wikipedia and so on. So once this data is generated, now people have run these AI algorithms and come up with new ideas to recognize the patterns and so on. And now we can use AI to generate the code. So this is what we are going to learn, and currently where the world is moving towards is something. So if somebody asks what is your favorite language, or what is the language that you should learn in coming days, it's not C or C++ or anything. It's the natural language, which is English, natural language, and you can tell what to build, and it would create default program, and then on top of that, you can keep refining it. So I'll just show you one thing, like how you can get rid of this. So I have asked you to install a software called as Cursor. So this is like an empty um, project. So I'm going to create an open project, and probably I'll create a new folder, demo. By the way, this Cursor, so I was talking about VS Code, right? VS Code is an open source, Microsoft has open sourced it. And this is a clone of the Microsoft. So you can simply, if you have used VS Code, this looks similar. Okay. So what this has is, so if you try to understand the structure of any given editor, it will have list of files. I'll just show you how an editor looks like if you haven't. I'll just open VS Code. VS Code. So this is how typically any code editor would look like VS Code, or you can use um, IntelliJ or whatever it is. So generally, you would have some files, say something like this, folders, and then you have some more files inside that for structure and all these things. And then you have the code. So if you want to write a new program, you'd create a new file, and then you type new file dot py, or whatever it is, Python. This is Python file, and then you start writing the logic here. Okay. And this is how we used to write. So VS Code was like a blessing for us because we moved from like VI editor and non-syntax highlighting editors to this was like a new thing, and this made our development time probably 5x better. But recently, if you look at this, so this is where you can ask. Let me just highlight this. So we saw that there are mainly three panels. One is your files, and then there is in any given AI editor you have a chat bot. So here, and you can ask anything. So let us. I'll just randomly think about some idea, and then I'll show how it works. So I'll tell it to say, I want a program which can generate random numbers in Python. Okay. So it created the file. You can see that on your left side, it created a file, and then you can go back and say I to generate random numbers using this program. Say I want to generate, and also it autocorrects. Like if you say grammar mistakes or typos or anything like that, it will do that. I want to generate 20 random numbers using this program. So it understands the context, and it is making the changes. You can see that it just made the change here to the program, and you can simply accept the changes without even writing a single line of code, and you can simply execute it. So you can say execute, and it would, just like a software engineer, it would go to terminal and it would trigger the command to execute. And yeah, so now the settings I have put as ask every time you run a command, so that I'm in control of what it is running. Now you can see that it ran into an error. So command not found Python. So, and it also guessed what could be the solution, and without me prompting it. Now it thinks that, okay, Python is not there. Probably let me try Python 3. And it is able to generate the random numbers. Now, this is like very simple program. In fact, now people are building, if you had to SaaS products, which is like software as a solution, you can build something like, say, like Facebook, Twitter, or your own Reddit. You can simply build on your own. But why, if these programs or if these editors, if they can generate the programs like this and without me writing much, uh, what is the need of software engineers? And anybody, like any student, or can any researcher do this? Okay, so that's the question, and people are trying to do that, and some people are getting better at that. So what is the um, differentiating factor that helps us to develop in a professional way, and in a professional in the sense that you can control the program, what is the program and what are the components of it and how they communicate with each other, the components, and then how it is going to deploy it. So if you're not in control, what it would do is it will just keep on generating programs. It would randomly create a website, and it will guess the features that you want. And once you have a sizable amount of code and you want to modify something and you want to understand, you won't be anywhere closer to the completion, because it's like getting into a forest without having the map. So what, how should we think about going, developing anything is, like you should, there are several patterns. So you can remember the pattern, something like you have to plan, you have to like brainstorm, and you have to like test it, and you have to like add a feature on top of it and then repeat again, right? So unless you have a plan, you cannot do this. And this particular place where you're going to ask for generating programs, right? So this particular place is called as a prompt. So unless you know about how the prompt work, you won't be able to do that. So in order to generate or in order to create any application, you need to know how to plan your work and what is the structure, which is called as like software design. And then you need to understand what to ask, and you need to give the context. So this is called as prompt engineering. And in coming classes, I'll tell you like how to set the prompt context, and what does actual prompt engineering mean, why it is called as prompt engineering. So, has it has become a new subject, and how does AI interpret this? And if you have like, there are several models, right? Like ChatGPT and Perplexity, the Cloud, like, and then like there are so many, right? So each of these prompts are ingested by these large language models, which are called as LLMs, and they give you something which they think that is correct. So in order to optimize your output, you need to ask specifically, and you need to ask in a way that you get the right output, right? So this is an example. So now we have reached from a simple program where you used to like open up a notepad and write and remember the structure and all these things, and then you can write the programs. And now you can simply ask and just get it done. So if I want to say make this web service, something like this, if I ask it, so maybe there are like a lot of ideas that is popping in your mind, and then you just want to randomly ask, just like I asked. So it is doing its own thing, and then I can say build UI. So it will build a UI for this particular thing. Okay, and then it will create new directories for you, and then it will do whatever that software engineer does, and it will just keep creating. But you need to understand, before programming, you need to think about what you're going to write, or else you'll be lost in a forest, or in a, like, you're on an ocean, and then your boat is there and you have a lot of things, but you don't know where to go. So that is what we are going to learn. And if you learn why Python is an easy language to understand. And once you learn as one language, you will see the patterns in other languages, and you can probably read through any code that is given in front of you. So and for example, let me just say, for this, explain this program. You can take any program, feed it into this, and you can generate the documentation. So everything is on our fingertips. So what we need to learn during the course of our entire course is, how do we plan before writing the code, and how do we connect the dots, and what are the components, such as like sending a mail, it could be scrapping a website, it could be reading a JSON file and generating something, interpreting a CSV file, or anything like that. So each of these components, we will take one concept at a time, and then understand it to an extent where you can start writing or generating the program. So overall goal should be, you should not be writing any of the code, but you should be having a plan, feed the plan into this and iterate over it. And then you get a lot of ideas, and also give any given point of time, a software can change because the features are always like, you could come up with new features, or if you are a company, um, people could ask for new features. For example, I just generated random numbers, and then there are like a lot of ideas popping out of my head. Oh, can I use this for, say, some game where you roll the dice and you can generate some numbers, like we play like snake and ladders or anything like that. And this will be a important component to do that. And you can ask, can I use this for, you can keep asking it, it will keep generating it, but you need to limit your creativity to an extent that you build something which is tangible and which is in your control. So two things that is most important that we are going to learn during the course of our course. So one is planning, second is prompt engineering. So, and then side by side, we'll also learn about Python, like basic control flow, like if else conditions, for loops, structure of the program, such as functions and files, modules, and all these things. So once you learn this language, it's similar to other languages. For example, it has generated HTML here. So once you learn that language, you can see that, okay, there is component inside component, and you can just read through it easily. So that is where we are going to reach. So by the end of the boot camp, we should be able to develop a SaaS. SaaS is nothing but software as a service. So the service that we are trying to build is, so it will give a news digest, and every morning at 8 o'clock, you'll receive whoever is a subscriber, they will receive news, and they will receive news about the weather, and so on. And we can add more features. And it's amazing how fast we can build things. So yeah, so this is what I wanted to demonstrate. And these are the things that you need to keep in mind. So how the computer programs run, and infrastructure. So remember that we went from monolith to containers, and you saw the data center, and each of the data centers rack has a lot of like pizza boxes sort of a thing. So where you can slide in the computer. So all of them are like chips. So each of them are like as good as your MacBook, or probably more powerful than that. And then we discussed about a development environment, and we'll discuss about code management, which is nothing but Git, and we'll discuss about deployment as we go. So development environment, today we don't have to type like today, in the sense that probably like from last couple of months, people don't write programs on their own way. So they just ask the prompt, they generate the code, and then they keep on iterating it. So building is most important. Learning the syntax, or learning the specifics of the language, or reading the documentation of a particular language is no more needed. So we will write program in such a way that you don't type at all, but you need to ask this large language model. So that is what we are going to learn over. So once you build something tangible and you get a pattern, and we'll get used to a pattern. So I'll teach you about like how to design, how to go about designing a software, and what are the components, what are the generic components, and so on, right? So each of these we'll do in our class, and you sort of develop a pattern. So by the end of the workshop, and then you can use that pattern to build anything. So I want you guys to build anything that comes to your mind, because now the programming language itself is not a constraint at all. Anybody can build a program now. Like if you're a researcher, if you're coming from a financial background, you have an idea. For example, you have your bank statement, and you want to analyze your bank statement to cut down, unnecessary spendings. You can simply feed that PDF into your program and ask and have a design like how to parse that PDF, and how to generate your dashboards and or suggestions or whatever, and feed that design into the prompt and see what you're getting, and then iterate to an extent that you reach the goal. So that is what we're going to do, right? So yeah, welcome to the bootcamp, and yeah, let me know how it was useful. You can ping me anytime. So you just install Cursor for now. There are several tools. So Cursor is just one of them. So you can try like there is Windsurf. There is I have tried GitHub Copilot. There is Codium. There is also now you install the IDE on your laptop. There are also several tools where you can build on the cloud. Like you might have heard about Replit. Like there are so many tools now. So you can just go on to the cloud and you can ask, it will just build an app. So over the last weekend, I built a SaaS product, which is like almost working within like what, 2 days. So it used to take, I'm not going to like lie about it. It will take about 6 months to 1 year to just to build that. So that is how much advantage that you are going to get out of AI. So like you can have an year project which can be done in a year. You can do it in probably a couple of weekends, and you can, as a one person, you can run a company. Like you can, because having this sort of help or this sort of LLM supported ID is like having like probably top 10 coders in your team, and you're just like a manager or a software architect to tell them, and then they're working like 24/7, right? You can build companies, you can build whatever you want. So yeah, I'm looking forward for ideas, and I hope you guys build something and then excel in whatever you do. Yeah, it is. I just want to demonstrate this. So, and then from tomorrow we'll start specifics about Python, and then we'll use AI to generate programs and understand what is happening in the backend. Okay. Yeah. Thanks, everybody. Yeah. See you tomorrow.
Thanks, David.
Thanks.